Thank you very much. And maybe just a very, very brief introduction to the session. This session is called End of Waste, Circular Economic Substitutions, New Raw Material. I think this all stems back sort of to in the morning when the very first slide Alan showed was Tokyo with a lot of material stocks and which eventually will not be sort of get out of use, and then what? And I think this panel we will really try to understand the so what or then what question. And in general, knowing also that secondary or reused, recycled materials make so much more sense from an embodied energy perspective, etc. How can we get there? So it's all about circularity of different building materials. I'm really excited about hearing all your insights. As our first speaker, Eva Gladek, she is the founder of Metabolic and has a background in biology, but also in industrial ecology from our own industrial ecology program at Yale. We are very, very happy to have you. And she has created an amazing organization that is really at the forefront of anything circularity, sustainability, at both industry level, research level. So thanks a lot, Eva, for being here.
Well, it's great to be here. I think I'm going to talk certainly about materials and their replacement potential and all of that, but also get a little bit into the systems mode because that's what Metabolic, my organization, is all about. Oops, that's the wrong way. My apologies. I'm going to first tell you really briefly about Metabolic a little bit more, and then tell you a little bit about my personal background for how I got into this. Then I'm going to get into some more detail on material demand in construction, and a lot of what I'm going to be talking about is from the EU perspective because we've done quite some research projects in that space. Then I'm going to talk about the potential for circular and regenerative strategies that we've seen so far and their limitations, and then get into what I'm seeing as kind of the next wave direction of how do we break through some of those limitations, maybe by extending the scope of the problem space. So first off, Metabolic is a systems change agency. For those people who actually know what industrial ecology means, I often say it's an applied industrial ecology organization, but most people don't know what that means. And the mission of Metabolic is to transition the global economy to a fundamentally sustainable state. Basically, we're trying to bring the economy within Kate Raworth's donut framework. Just a couple of weeks ago, I would have been showing you a very different diagram here. I used to have a slide here that said our ecosystem, and I showed 5 different organizations and how they interacted. But because of a very challenging last year, and this is also something that I'm happy to talk about in the context of what's going on in the world more broadly, we have been going through a very intense slimming down and restructuring process, but actually, in a way, it's something that brings more focus and clarity in terms of what we're doing. And what I can now summarize, the essence of what we're doing is there's the piece where we're doing advisory and research, so really generating high-level insights, doing a lot of Earth observation, policy inputs, et cetera. And that feeds into, in a continuous loop, our implementation practice, where we're really on the ground developing projects. And the idea that we have with this is that if you create this kind of elevator between really on the ground, roots in the ground, all the way through to the shoots of the trees, you create this learning flow. And you start to identify places in the system where you might be able to intervene more effectively, areas for leverage. And so over the last 12 and a half years of Metabolic's existence, it's been like this amoeba, continuously growing to identify those areas of leverage and then sometimes shrinking back. And we're now going through this very refocusing phase as well. I keep doing the wrong thing. Okay. So I'm going to do this quickly. And actually, this morning, there are some things I'm going to be repeating. Maybe it's good for reinforced learning, but I'll try to skim over those quickly. But just to tell you a little about my personal story. So I started out with the idea of becoming a biologist. I started working in labs at the age of 14. And one of the things that I did a lot of was grow E. coli in flasks. And so this is a cloudy flask full of cells. And this one is clear because it's a fresh flask of medium. And in the experience I had in the lab, I had this very visceral experience of the power and nature of exponentiality. Because I would take a sample from this cloudy flask and put it into this clear one and wait for 24 hours for the cells to grow. And it seemed for the first 23 and a half hours that nothing was happening in this flask. And then the last half hour, of course, because the flask goes from being half full to all the cells being dead, according to this exponential curve, it was like a flash. The flask would be a perfectly safe, habitable, flourishing environment, and then an entire wasteland. Now, I didn't think about that so much. I went to university to study genetics, and I took this course called Extinction, which was a distribution requirement, and I ran into these graphs. And they're the same exact hockey stick curves. Positive feedback loops in any system are very, very difficult to stop, and they eventually hit a ceiling and crash. And I got really worried about this. I was like, okay, so is there an Earth dashboard? Is someone making sure we're not hitting the ceilings? And actually, where are the ceilings? And that led to an entire shift in my career. So obviously, the Planetary Boundaries Framework tries to define where those ceilings are for key Earth systems, and we've crossed most of them. And this then became my overall mission and why I set up Metabolic. So I'm going to gloss over this. You all know this. We're crossing tipping points at alarming rates. And this is also leading not just to environmental, but also social, economic crises of different types. The political situation that we're seeing can almost be seen as an exponent of this. Alan already had this awesome statistic this morning. So in 2020, for the first time in history, we crossed a very questionable milestone, which is that for the first time, man-made products outweighed the total mass of all life on Earth. And this is the dominance of humans as a planetary force, and these exponential growth curves is largely driven by this material extraction. So we have continued to extract material from the planet exponentially. This is also differentiated here per capita versus in absolute terms. And we can see that it's quadrupled since 1970. And in the first year of Metabolic, actually using this kind of idea that materials are the kind of driver of so much of the impact and the crossing of these planetary boundaries, we made this very primitive at the time global material flow analysis. So this is 2011 data. And it's a Sankey diagram. And I'll just point out a couple of interesting things that are relevant for things I'll say later. Here at the end, you can see how much we're composting and recycling, so barely anything. A large part of the material that we're extracting actually ends up disappearing. It gets dispersed through being burnt or abraded into the environment, or painted, for example. And then also, this was already mentioned, a lot of material ends up in stock. So even if you were to take all the material that we're disposing every year and imagine looping it back around to the beginning, you're actually only closing a very small amount of that resource cycle. And that's because we're continuously increasing the amount of material that we need because of growth of the economy, of our population, and also just because of the nature of how this material gets distributed. Now, I'm going to probably repeat a few things that you heard this morning. But zooming into the built environment specifically, we did a study for a group called Built by Nature, and we also co-founded an organization called the Circular Buildings Coalition. And a lot of the data I'm going to show you is from research that we conducted for those initiatives. So in the EU, the construction sector consumes approximately 1 million kilotons of material, which is around 100,000 Eiffel Towers every year. This is a breakdown of where that material is going. So you can see the difference between residential, sorry, I keep pressing the wrong button, my apologies. The difference between residential up top and commercial utility buildings. And as has already been mentioned, the vast majority of this material is concrete, and most of the material is mineral-based. In terms of regional differences, most of it in Europe is going to Western Europe. And again, this points to these disparities that actually, this isn't a requirement, it's a choice in a way. It's policy, it's the way we design our buildings, it's how we choose to live that's determining the size of this footprint. Because of course, they still have houses in Eastern Europe. Am I going the wrong way again? Okay, so then again, as I mentioned already, most of this is used for housing. And actually, increasingly in Europe, more and more is going toward low-rise homes and single detached houses. And here you can see roughly how that looks by country. And then if we translate that, so what we did is we actually downscaled the global planetary budget boundary for carbon and looked at what that would be for Europe, and then specifically what that would apply, what it would look like for the construction sector, which is 2.1 gigatons. And this research was done 2 years ago. So before we knew that we had already crossed the 1.5 degree temperature increase, and based on our knowledge at the time, the carbon budget for the construction sector would run out in 2026. And so here you can see in this graph the carbon budget for different so actually depending on what temperature increase you're talking about. So 2 degrees was supposed to be in 2032, but now I really also don't believe this because the situation around us is changing so rapidly. I am clicking this. Okay, I don't know what happened. Keyboard? Okay. That's not working. Okay. Is it this?
It's working, yes.
But is this? Oh, yeah. Okay. Now let me see.
So it's a picture.
Okay. All right. I think I was right. Okay. So now onto the question of this whole section of the panel. So we're talking about the potential of circular economy strategies and regenerative material use as a solution to this entire set of problems. And I'm obviously not going to get into all the details, and some of this has already been touched on, but to look at a couple of points. What would happen if indeed, as has been discussed in various roundabout ways and direct ways, if we substituted most construction materials, and specifically concrete, with bio-based materials instead? So we did a kind of in-depth analysis, again, looking at Europe, and we looked specifically at residential construction since that's the priority area where the most construction is happening. And we looked at the time frame of 2023 to 2030. Now, we had 4 scenarios, and this top scenario is actually a very ambitious one, where 100% of construction by 2030, new construction, would be bio-based. And the second one below that is 50%. By 2030, so a kind of linear extrapolation from where we are, which in Europe is starting at a decent 10%. Now, what we saw is that the reduction potential just in terms of carbon emissions for the max scenario, where you go 100% bio-based, was around 40%, which is pretty good. It's around the same as 240,000 rocket launches. And in addition, as we've talked about, there's the carbon sequestration factor. So the carbon sequestration, which you would calculate over a 30-year period, would balance out the embodied emissions from the construction completely in this scenario as well. However, I have to say that this is a very unrealistic scenario. Actually moving toward 100% bio-based construction, and we used a relatively simple model, is quite unlikely to happen. Furthermore, this would require a 10 times increase in absolute terms in engineered wood production. Now, of course, this is all assuming business as usual, the amount of construction that we're currently doing, just simple extrapolation. And where would that wood come from? So this is where wood production is currently happening in Europe. And this would require adding a harvest area around the size of Finland to this entire thing. Now, there is room for expansion of wood production, but not enough under the current model to cover this entire extent of the 100% scenario. And one of the things I was having a very interesting conversation with Mark last night about these very issues, because it does seem like these types of calculations are often made in a very straightforward way, and then the idea of moving to bio-based materials and construction is vilified, when actually we are very much misusing those materials. And we know that there's huge efficiency gains. We've already heard how much material is wasted on construction sites. 30% of the wood that goes into a construction project isn't ultimately ending up in the building, et cetera. But another thing that we've seen is that working across many different sectors, almost every single one of them is saying, oh, we're going to go bio-based. We're going to replace our current fossil feedstock, or we're going to go away from plastic bags and straws to paper products. Everyone is actually converging on this space, and none of them are talking to one another. So there's all of these different parallel sectors, and even if you solve this problem for one sector, say the built environment, you have all of these other ones that are not actually communicating with one another about this challenge. So a second question, if we talk about maximizing material recovery from existing building stock, this is another area that we've done a lot of work in. There's this whole idea of the urban mine, which we've also heard about today. So huge amounts of value in material. We saw Tokyo, this massive urban mine, and almost none of that value is being leveraged at really high, at its greatest capability. So we designed actually a tool that works, again, mostly for Europe, that allows us to predict the amount of supply and demand of different materials in existing building stock. And we've done a lot of ground truthing on this, et cetera. So it's called the urban mining tool. And we started working with different governments, both national and city, to help predict when and where building materials might become available and matching that with new construction projects to figure out where you might put optimal locations for storage facilities. But again, even if you do this and you go through all of this trouble, you're only potentially displacing up to 12% of virgin material demand under current situations, right? Like, we haven't optimized existing building stock for deconstruction. Economic recovery of these materials with existing technologies is challenging. So this result, which is from the Circular Buildings Coalition report, is based on those findings. So there's lots of different things we can do to improve the situation. We obviously can redirect existing material flows to higher value uses, really focus on avoiding burning wood, though as far as I know, the IPCC models really rely a lot on biomaterial for energy in their decarbonization pathways. There's room for creative new bio-based products from other types of trees, actually, which can result in a broader range of engineered wood products. We can also develop better monitoring systems. We can steer toward more sustainable forestry. We heard a lot about the importance of actually high quality, healthy forests, especially in the face of the changes that we're seeing with climate change. And either way, obviously we want to push for circular and bio-based construction techniques, but these results, even just these two preliminary things that I've shared, to me clearly indicate that this is not enough. We actually have to really structurally look at reducing demand if we're going to be tackling this problem fundamentally. So my main conclusion from all of this, and which is what I've come to over the years, is that we need a broader portfolio of systemic solutions, and we also need to be looking outside the kind of narrow scope of certainly material substitution. Now I'm going to quickly share with you one area where we've been doing some applied work and how that's now led to the conclusion that I have come to around this. So in Amsterdam North, where we're based, in the first year of Metabolic's existence, we set off to build a circular economy living lab. We got the right to develop a polluted brownfield, a shipyard that had been left with a lot of remnants of oil and paint, and we won a competition. And to make this work, we upcycled whole buildings. So we eco-retrofitted old houseboats, which you can see here. This pointer doesn't work. And craned them onto the land. And we actually turned this into this whole playground for circular material use. And really, over the last decade, we've done all sorts of testing of different flows. The other thing is that we've also really very practically and hands-on learned what it means to take old wood and recycle it, or to take old gypsum or whatever, because we did that physically with all of these buildings. This project was so inspiring and such a success. We've had visitors from over 50 different national governments, that the city of Amsterdam actually asked us to develop a broader circular economy strategy. And again, this is not working. So a broader circular economy strategy for the area around that, called Bouwsloterham, a much larger area, 100 hectares. And this ended up changing policy in the city, because after developing this broader strategy, they asked us to develop a whole set of rules for new developments in the city. And this whole area signed a manifesto that any new project developments there would be more circular and bio-based. And now it's the first energy positive district in the Netherlands. Jeez. And you can see some of the later projects that we got involved in. So this is Schoon Schip. It's a floating housing development with many different innovative buildings that have all been designed in a circular manner. And in general, there's been like 35 different cutting edge projects in this area. Now, looking at these kinds of place-based transformations, one of the things that I've come to realize is that you have to really look at them as whole systems transformations. And this has already also come up today. How do you look at the context, the existing resources and capacities, and start to figure out how to optimize flows over time? And what does that mean in terms of land use and what we're doing with land currently? And what does that potentially mean for building demand? So currently, this is roughly the distribution of land. We have 3% for cities, which are like these massive drains where all the resources are ending up, 38% for agriculture. Then we know that there's around 23% wilderness, and so the remainder is like land that's been impacted, but not like urban sprawl of some sort. Now, what it could look like is something more like this, potentially, where you have green cities connected by these mosaics of different types of land use, recreation, energy generation, and extensive farming that's done in a regenerative manner. And you can get there progressively over time through different zoning practices. Now, how this connects to really looking at demand for building materials is that there's a massive imbalance in where buildings are being used and not. So in 2019, 16% of the population in the EU lived in overcrowded dwellings, though in some places like Greece, this was up to 30%, whereas 35% of buildings were actually underoccupied, and many were not occupied at all in rural areas. And earlier today, we heard this statement, and maybe this is true, that we're inevitably progressing toward more urbanization. But maybe that doesn't have to be true. Maybe we can actually envision through a set of mindset shifts, through policies, pathways where we actually start to reclaim whole bioregions in place-based transitions, where we're looking at building from the ground up new kinds of bioeconomies that are also focused on multi-solving. So rebalancing housing demand, allowing us to actually use existing building stock, alleviating loneliness and the mental health epidemic. I don't know how many of you have seen this blue Yale magazine. The main cover thing is about mental health and students. Supporting the development of future generations of farmers, because we barely have farmers anymore, and they're all old. So there's all sorts of, and also very importantly, laying groundwork for regenerative industrial value chains that can also supply those materials in those places. So there's a huge emerging movement that we've been monitoring around the development of agro-hoods, bioregional hubs, and circular material processing facilities that could potentially serve as these anchor points for these bioregional transition efforts. And I think that this directionality, if you expand the solution space rather than just focusing on the material side of things, starts to open up more possibilities. And again, I just leave you with this one image. I use this Rubik's Cube picture a lot because ultimately, if you just focus on the one square that you're trying to move, you scramble the whole cube. You have to look at it as a whole and look at all those interacting parts. Thank you, and I look forward to the discussion.
Thank you very much, Eva. This was great. Our next speaker is Catherine de Wolf. She comes from the ETH in Zurich and is a professor and also design in circular architecture. And we'll talk about digital management in circular chemistry.
Hi, thank you so much for inviting me to speak. I'm very honored to speak right after Eva because I'm a big fan of your work and metabolic, and I'm also a big fan of Yale and the work you do here. So I'm going to talk about it's indeed not very intuitive, the order of the... I'm going to talk about digital management of the circular building economy. And to talk about that or to illustrate that, I want to show you two examples. Does anybody recognize this building? You can speak up because I don't see you. Seattle, yes, great. All right, it's the Kingdom in Seattle, built in the 70s. And it was at its construction, it was the largest concrete dome in the world. It was designed to last 1,000 years. Maybe this makes you think of another concrete dome that has been standing for 2,000 years. Yes, the Pantheon in Rome. So it's really possible to build a building that lasts 2,000 years. But this is what happened to the Kingdom only 26 years after its construction. So maybe we can treat our buildings a bit differently and treat our cities as a mine of materials, a bit like Eva was mentioning as well in her work. Does anybody recognize this city? Yes. So this is the city of Paris. I had the chance to work there for an engineering company called Elliott. Maybe you recognize also the building that's showing up. Yes, yeah, that's usually a quite famous one. And I had the chance to work with the engineering company that was doing the renovation of this facade that is very famous for its bent glass over these escalators and these hallways, which are called la chenille in French. Chenille means caterpillar because of the shape of this structure And unfortunately, when you renovate, you have to abide to the new norms, and we had to throw away all of this beautifully bent glass. So I went on a mission to find a new home for this glass, and after calling my entire network and having the help of the whole engineering company that I was working with, we found this project here, which was designed by Maximum Architecture. And this project is called Papillon, which means butterfly in French, so the caterpillar could become a butterfly. And I really like this project because it showed really that when you care about the materials, that it's really possible to put in all of the efforts to reuse the materials. I was sure I would find at least someone that wanted to reuse the glass from the Centre Pompidou. But how do we upscale that to all buildings, not just the famous buildings? How do we transition from a linear economy model where we extract, produce, use, and dispose of our building materials towards a circular economy model in which we use our buildings and our building materials longer? So I do a lot of research on each of the steps in the circular economy. I start with auditing the existing building stock, to see, a bit like Eva was saying, also to kind of predict patterns of reuse where building materials will become available for reuse. Then I also do research on the actual disassembly process, on the design with the reused materials, and on the assembly with the reused materials. Now, we calculated together with the other engineers that worked on the reuse of the glass from the Centre Pompidou how much time we spent on calling and emailing so that we could make this reuse happen. And it turned out that we spent about half an hour per kilogram of glass that we reused, which, when you know it, the billable hours of engineers, it's not very efficient. So this is not really an upscalable method to ask engineers to spend so much time on making the reuse happen. So when I started my lab at ETH Zurich, I was wondering, how can digital management maybe upscale circular construction? I did my PhD at MIT, not so far from here. It's really nice to be back on the East Coast. There I learned a lot about digital technologies, and then I went to ETH Zurich, who is also really into digital fabrication, extended reality, and all of these kind of digital technologies. And I thought, can I maybe harness the power of these technologies to upscale circular construction? A bit like you were saying, Eva, that in the current state of technology that we have now, maybe we cannot reuse so much materials, but if we develop more these emerging technologies that we have today, maybe we can upscale that percentage that you were talking about. So I'll talk about the technologies that we develop on auditing, disassembly, designing, and assembly. But one hopefully key point that you will remember after this talk is that in each of these steps, what is the most important thing is the matchmaking between the different stakeholders that we're working with. And I think afterwards we'll have a talk also about systems thinking that will, I think, confirm it. I haven't seen the talk yet, so we'll see. So let's start with the first step, auditing. So I'm asking myself, how can digital management improve pre-demolition audits of existing building stocks? And here are a few photos of a few of my lab members that work on this question. And this is a photo from the PhD of Deepika Raghu, who just defended her PhD in my lab. And she's working at looking at GIS data and image-based data so that she can predict these patterns of reuse. So she looks at historical photographs, social media images, real estate images from real estate platforms, and also Google Street View. And so here you see, for example, this image from Google Street View. We can use computer vision to classify that this is a brick building, or we can detect the number of windows in there or the area of the different materials. And so the ultimate aim is to build a global resource cadastre where we can really detect which buildings are going to be demolished and how we can make an assessment of the materials that are in these buildings and in what condition they are, so that we can reuse them in buildings that are being built or renovated. I'm doing this with two of my previous lab members who are now at Stanford as well, as with Deepika. So once we have looked at the urban scale, we also zoom into the buildings and we go into scanning technologies like LiDAR scanning, where we have more accurate information about the buildings. And then I actually like to disassemble the buildings with my students because I think we learn a lot from that. This is a building called the Huber Pavilions, which was on our campus. And anybody who studied architecture in Zurich knows about this building because it's very beloved by architecture students and professors. I also wrote a book about this building and about the process of disassembling and reusing these materials. So we reuse 30% of the materials of this building in different projects. Yes. And so this brings me to the second step, which is really the disassembly, and how digital management can help disassemble existing building stocks so that we can reuse the materials instead of the landfilling or the burning that we were talking about earlier. This is me disassembling a pipe in one of these buildings that we disassembled. So we try to identify buildings that's for demolition, and then we go and try to save as much materials as we can. These are two of my PhD students disassembling some OSB plates. That was my first month, I think, at ETH. So I did it very manually, but since then we evolved a bit towards more digital disassembly. So this is the work of Zane Carson, one of my PhD students, who is really looking at how we can use robotics also to make the disassembly process safer and more automated. So here again, he uses point clouds and machine learning, computer vision to detect also which parts of here it's a simple setup where we just wanted to detect the weld, so we cut precisely where the weld is, but we are working on upscaling that on a bigger building scale. All right. I think there's just a little bit where you can see the cutting. Yes, here. So here it repositions itself and it knows where to cut to disassemble this piece. Once we've disassembled all of these materials, we need to track and trace them. And this is not a new concept. We've always had ways of tracking and tracing materials. For example, brick stamps that one is from the Babylonian times. So it's really an old concept, but today we have digital technologies like QR codes or chips or even DNA tracking, which we are working on in the lab to link the materials to digital product passports. All right, so we did that also with the materials from the Huber Pavilions that I was mentioning, and we built several buildings and structures with my students, which won several awards for the tracking and tracing of these materials. Here's another building we disassembled with my students. It was a 2-story timber building disassembled in 2 days with 20 students. And then they designed a dome structure with it. And again, this is then the third step of my work, where we are looking at how digital management can play a role in the creative design process. So we're looking also at generative AI. This is the work of Vanessa Schwarzkopf, who did this in her master's in Hanover, where she fed the generative AI tool a bunch of facades, and it's dreaming up facades. And I always say this is not a facade, a bit referring to a Belgian surrealist painter, René Magritte. I'm from Belgium, so I like to refer to him. But because it's not really the idea that we are going to use generative AI to design our facades, but to help us in the creative process. And we do this together with Trazando Espacios Públicos from Venezuela, where the children are drawing what they want their buildings to look like. And we're building, in this participatory process, we're building a structure with that in the Venice Biennale. So I cannot show you pictures yet because we're still building it. But if you're planning to come to the Venice Architecture Biennale, we'll be there in May. One thing that I can show you is the project we did in the Museum of Modern Arts in Zurich, where we were working also with children from the schools in Switzerland and making drawings and then feeding it to generative AI to help us in the creative process. But then the challenge is to make something constructible. So my students then made a structure that is constructed and that is now being built for the school children. And then the last step is about assembly. So here we use digital fabrication, where we are looking, remember these pipes and these OSB plates that I was disassembling in the first, so we did some digital fabrication so we could turn this into a connector. And we're also using extended reality in order to be able to assist with the assembly of, here in this case, a wall with concrete rubble and concrete cutting waste. And if you want to play with this, you're welcome to join the Sustainable Built Environment Conference in Zurich in June that I'm co-chairing, and we'll do this also with robots there. All right, so that brings me to the conclusion. I mentioned that what was really key in each of these steps, or really the bottleneck in each of these steps, is really the matchmaking. We need to connect the different stakeholders with each other. That's also the title of my latest book, The Art of Connecting, that you can access through the QR codes. I also brought a few copies here. And I want to end with a picture of my lab members, because I always say creativity comes from the art of connecting. And each of these members are from different parts of the world, have different backgrounds. They range from anthropologists to computer scientists, architects, engineers, and so on. And I think we really need to work with all of these disciplines together if we want to upscale circular economy principles. Thank you very much.
Thank you very much, Catherine, for this nice overview. Our next speaker is Jennifer Russell from the Virginia Institute of Technology, where she's an assistant professor of circular economy and also focuses sort of on circular material and energy systems. Welcome. Thank you.
Thank you. It's a great honor to be here in this audience, and I appreciate everyone's time and panel members. I fear that I will be repeating many of the ideas that have already been presented. At the same time, repetition is great, and I promise that I will bring some nuance to this. So I might have to, there we go, beautiful, okay. So I'm gonna be talking today about this other idea that stems from industrial ecology, urban and industrial symbiosis, and how that theoretical approach and concept can feed into a lot of the work that's being done from design of systems and products and buildings and human relationships, but also what we already know that we could start to leverage a lot more effectively and efficiently. So before I get into this though, I think a current state synopsis of circular economy is a really important thing. We've talked about this idea of circular economy. As somebody who studies this and spends a lot of time exploring, I cannot give you a definition. One of the challenges with circular economy is that there are over 150 definitions that have been proposed. There is very little agreement on what the right word is. There's different concepts about whether this is just about recycling or whether this is about a sustainable future that encompasses the biggest boundary that we could imagine. And so without that consensus, it leaves us with as academics and researchers, the challenge of, well, let's keep pushing at this problem. Let's try and refine it further. Because of this complexity, we run into an implementation problem. And that's where I spend a lot of my time. I actually spent 10 years in industry before I went into academia and research, and I worked with consumer packaged goods companies. They were trying to figure out, what is sustainability? Why do we care about this? Do we really have to? And if you lived in a country that was implementing extended producer responsibility laws, they did have to. And there was still this resistance, this human challenge of accepting or understanding. Diverse languages, not capital L languages, just languages of the disciplines and the training and the cultures and the communities we come from are creating some huge barriers. So we have this escalation, acceleration of ways that we talk about this idea of circularity, and it leads to maybe more conflict than we really need. One thing that is thankfully common is that at the very least, we all agree recycling should be a part of this. The challenge with recycling being the only common narrative is that recycling happens at a material level, right? And very few things that we have in the world are actually just a material. They're always materials that have been synthesized and improved and stuck together and assembled into a variety of things and used in a variety of ways. And even just looking around this building, this room itself is a fascinating example of this, because you can see the gravel in the wall, but you can also appreciate that you can never extract that single rock. So what's relevant from this huge overarching effort to look at circular economy and think about what it is we've agreed there's really actually not a one-size-fits-all solution. No matter what product, category, sector, portfolio you're looking at, it will require a nuanced and different approach. So that's good. No, we know going into it, it's going to require some customization, and standardization is actually a path we should maybe not be preoccupied with. But framework approaches, standardization of how we can think about this. What is the trajectory that we are aiming for? That is a really important thing. Even if all we can do is agree on, well, we want it to in some way resemble a circle, that's a really good starting point. And it is not necessarily something that everyone agrees on yet. We also need to recognize the roles that cooperation and coordination and integration of complex networks. That's been said many, many times today. These are the things that we know and we can accept from the existing literature. But if you Google circular economy, you're going to find millions and millions of iterations, and it compounds some of the challenges we have. So rather than defining circular economy, I'm going to instead start with this lovely picture, which represents the inspiration of the motivating narrative behind the field of industrial ecology, the work that many people do looking at industrial and urban analogies for the natural environment. And before I get into that, I just want to really point out, it took me a very long time to find an image of this food web that included pictures in the middle that were not pretty and natural. Most food web systems will talk about the decomposition role, the destruction of living things with pictures of nice mushrooms and fungi and maybe some bacteria. But the reality is it actually is quite messy, and this is the blind spot that we have as humans. And there's an evolutionary response there. There's a good reason why we don't want to look at waste, the byproducts of being alive. We want them away from us and over there. And that's not a bad evolutionary thing to have happening. The problem is, though, we are intentionally stepping into conversations about circularity and pretending that that messy thing isn't part of the problem. When we talk about waste, it's maybe a bubble in a life cycle diagram that might be a really nice color of green so that we feel better about it. The inspiration behind circular economy is really this idea of ecological symbiosis. There is no such thing as waste in nature. There are many talks about forests today and how they are perfectly balanced systems. Every byproduct of everything in that evolved system has a corresponding consumer. There is no such thing as waste. All of those exchanges and interactions create benefit for some other actor in the system. And so at that highest level analogy, we've got this idea, if we really are truly seeking nature-based solutions and innovations, how do we mimic nature? If we can't acknowledge that we actually, as living creatures and humans, we generate these uncomfortable, not nice to look at, not nice to deal with things. So circular economy, if we start there, right? We've got these natural systems to inspire us. We have this idea of there's no such thing as waste, right? If there's no such thing as waste, what it must mean is that wastes are actually valuable inputs. or valuable feedstocks to some other system. And if we are designing anything and do not have a plan for the byproducts of that thing, it's the antithesis of nature. We are telling ourselves a very nice story, but it's not going to work if we cannot take it apart, if we cannot disassemble it, and if the thing that we finally smash into smaller pieces cannot be used by something else, the rest of it is kind of a moot point. So as a systems scientist, I work across all different kinds of scales. Many of you would identify here where your work focuses. At the lowest level, we've got material inputs, molecules, whether they're biomaterial or technical material, and it can aggregate all the way up to the global level. If we move up from the bottom to the top, the way that we build things and design them, we are assembling, constructing, and if we decide to go from the top down, we are deconstructing and disassembling. And the beautiful thing about some of the things we do in natural systems and everything around us is that they can go up and down and in circles, and they don't have to necessarily move in one direction. The work that I do is focusing on to actually move towards circular economy. We need to do this with some sort of coherence, some sort of coordination, and with thoughtful integration. So if we have this idea of a balancing table in the middle, we're aspiring to circular economy in the built environment. How can we take systems level views like industrial symbiosis and urban symbiosis to inform that type of integration? Just the same way that we would not build a structure or development in a space that did not have municipal water supply connections already planned or roadways, right? How does this thing we're building connect with everything around it? We can think of these industrial symbiosis integration strategies. From the bottom up, we also already know a lot of what's going on in the world. There are so many examples that have been presented today. How are we experimenting with circular economy? In many contexts, it's either at the material or the product level, but we know quite a few things already. So from this industrial and urban symbiosis level, the systems level view, we're really looking at how do we understand and create these types of exchanges, right? Rather than there being a waste that nobody really wants to acknowledge or deal with, how do we reframe this, recognize inherent value in whatever the byproduct is, and identify connections? And the matchmaking example that was just brought up was, again, really, really salient, really a strong point. This might be an ideal future. We've got to start planning for it right now. In order to make those connections, we need to actually dig into the flow characteristics that are happening. There have been a lot of beautiful diagrams. I apologize, I do not have these beautiful diagrams. The questions I ask about these flows is, what is it that's moving? You could do that at the most micro level. It could be, what is it that's in your garbage can that's going to go out to a landfill, right? That individual personal inflow and outflow. What is on your shopping list that you bring into your house? You can also scale that up and say, what is coming into this building every day? What is leaving this building every day? And if you want to go on a temporal scale, what is coming in over the lifetime of this structure or this space or this community or this economy? And what is leaving? Where is it going to? Have we actually integrated this? Are we creating a beautifully designed system that actually can't function within the space that it's being placed because they don't have the corresponding infrastructure or cultural practice? There's a lot of mismatch that's happening. When is it happening? Another challenge, right? The lifespan. I did a lot of work in packaging, for example, and we are designing amazingly designed one-use water bottles, plastic bottles that will last for 400 years. Arguably, they say that's an engineering, over-engineering problem. But the same thing exists in any product that we're making, any analogy there. How quickly are these things moving in and out? Perhaps we could think about slowing that down or designing it differently. And so this is where, again, I am not an architect. I'm a systems scientist, and I'm looking for these ideas. What can the built environment learn from the product environment? What can the products and materials and packaging environment learn from the built environment? It's come up a few times, this idea of life cycle. Integrating across the life cycle, recognizing that everything we have came from somewhere, transformed in some way, is then used, and it needs to go somewhere, not necessarily a landfill. So we've got these really nice life cycle diagrams. They are inherently linear because we have a really strong mental model as humans about how that might work. If we talk about sourcing, where these materials come from, it's been discussed a lot today. What I would like to emphasize is we have a lot of urban mining opportunities that are already out there. Do we need to actually go and take more from the environment? Can we come up with innovative ways to think about where we are sourcing all of the inputs that we need? The idea of designing for re-X. And if you haven't heard of this, this is any re-based word: reuse, repair, refurbish, remanufacture, recycle, redistribute, repurpose, whatever it is, it starts with RE, falls under design for re-X. And this includes really critical considerations: disassembly, how many service lives does it have, how might we test and run diagnostics on this to make sure it's not going to fail? Can we standardize that? There's some really good examples if we look to products that are already doing this. Automotive sector, heavy equipment. These things are being designed. Components in your vehicle are designed to have 9 to 10 service life cycles. Not many of them are actually getting that many cycles, though, because we've got some disconnects in the system. So if we look at this idea of product remanufacturing, we've got this application of circular economy. It's out in the world. The inherent idea here, if we look at vehicles or aircraft as our analogy, is the highest level of environmental value and the highest level of economic value is created when we can keep that product or structure intact, maintain its inherent functional form. Reuse, repurposing, recapture, at that level is going to give us the biggest bang for our buck if we are efficiency people. But at the very least, we have to recognize the midway steps as well. If we can't reuse the whole building, we don't want to automatically jump to recycling as being the only other option when there are many midway points along the way. So if we have a design priority for making things that their inherent functional form can be maintained many, many, many times over, and then once that is done, how can we disassemble it without destroying it to use those larger products, the modules, or maybe the components, at the very least the parts? Urban mining work is focusing very much on materials and elements right now, but that's also because we don't have design practices in place that let us keep the modules and the larger components intact most of the time. And inherent in all of this, as well, is even though we talk a lot about recycling, that should be the very last thing that we do. That's the thing we do when no other re-option is possible. And this is what we know from all of the practice and applied work that's happening in the product sector. The other thing I'll touch on briefly is shifting the mindset from things to services. At the end of the day, all of the structures around us, the products that we're using, they provide us with utility because we use them. So we can also reframe this to be service-based instead of thing-based. Right? I don't necessarily need to own all of my stuff. And if I don't have to own it, how does that change the whole system around it? How does that change the economics, but also the design imperative? It suddenly now prioritizes things like multiple service lives and durability and the connections and integrations that are part of the industrial symbiosis and urban symbiosis imperative. I love this picture by Eberhard because it really helps to capture the complexity. Whether this is a building, you've got a picture of a building here, this could also be a $500,000 generator at a mining site. All of the different components are going to have different lifespans. Rather than assuming they all have the same lifespan, perhaps we design and integrate accordingly. I will say, when the comment this morning about the carpet, spilling coffee on the carpet, I had a mini heart attack because a lot of the work I do is actually saying, how could we design this carpet system and the contract system and the service system differently so that if coffee spilled on it, we don't have to tear out the whole room and replace it? And so those what-if questions are really important. And my argument here, we have a high-level concept of connection and integration that we can design for. We also have real-life applied learning at the product level, and the packaging level, and the things that we're already experimenting with that can inform both. And that's what I really hope when we think about designing for the future, that it's not just about what new innovative technology or material we can use, but what do we already know, and how can we do that better? And the anecdote I'll add at the end of this as I close out, when I told my grandmother 20 years ago that I was going to start studying this really cool thing called circular economy, and she says, what's that? And I'm like, it's like repair and reuse and recycling. And it was the most humbling moment in my life, and I share this all the time. She said, that's not innovative. We've been doing that for hundreds of years. And I agree. And fundamentally, that level of humility and recognizing that we are a moment in time, we have so much to learn from past generations and from other countries and disciplines and practices and cultures, if we don't pull these things together and integrate the knowledge alongside the systems, we can't get there. But at the same time, we know enough that we actually have everything we need to start solving our problems. I appreciate your attention in true academic format. I give credit to my references who assisted with this.
Thank you. Thank you very much, Jennifer. Back to the basics. Our next and last speaker is Christian Gett. He's from Bauhaus Earth in Berlin. And he's an architect and is a material and architectural researcher, and really at the interface between practice, novel materials, and the whole theory behind it. And you've all seen some of his work with the bricks outside in that beautiful ceiling construction that's outside. Thank you.
To present the research that I've been doing in many different constellations over the past years. And I actually hope that this will be a use case that answers some of the questions that came up during the morning, considering wood maybe not as the silver bullet for solving this construction crisis, but also actually answering some of the questions that Jennifer just put up in terms of systems guide on understanding a circular economy. So I will be speaking more specifically about earth building and how using earth and mineral resources has an effect not only on the immediate built environment, but also on much larger overlaying systems that are also governing our existence here on this planet. But before I start, I actually want to ask you a question, because it seems like that Alan, Eva, and I read the same journal. So the question is, in what year did the total mass of all anthropogenic matter surpass the total biomass on this planet? 2020. And you can judge who spoke about this best, but I want to zoom in onto a specific idea here, because clearly we see a pattern on what kind of resources are mostly contributing to this. And this is asphalt, bricks, aggregates, and concrete. And it happens so that these materials are largely sourced from mineral resources, right? And to further look into this, I want to look at this graph, and this graph is showing how actually there's not only a great acceleration between the 1945 and 2015 in total material use, which you can see by the width or the thickness of the line, but also a shift in the kinds of materials that we're using, which you can see on the pie charts on the right, where biomass used to dominate up until the Second World War, really the main resource that we were using in order to produce the goods that we're consuming, the resources that we're using to build our buildings. And now we have really shifted to using almost 66% of minerals and metals to build our buildings. And numbers only speak so much. If we look at this in terms of architecture, it might look something like this, where this shift happened maybe around 100 years ago in Europe, where I took a picture of an old building also made from rammed earth, very, very close to Dessau, the famous place where the Bauhaus was funded 100 years ago. But in other cultures, and I've been also working extensively in Senegal, this shift is much more recent, and it is coexisting, where still the vernacular architecture is taking up the natural resources that can basically be sourced in a radius of 5 kilometers from the construction site, resulting in mud huts, which is then slowly being replaced now by an imported material, which is concrete. And the effects of that are quite clear when we look at the extraction sites. And this is a video I took while driving through a sand and gravel mine just outside of Berlin. But it could as well be the moon, right? It looks like a space that is almost out of the earth. You might just see the trees in the back, but really it is a scar in the landscape that we have created in order to feed our thirst for these materials. And at the end of the life cycle, we basically fill these scars that we have created by sourcing the materials with the rubble and the debris that is created through the demolition of buildings. And so if we look at this from a systems perspective, we really must ask what happens if the global building sector is consuming 84% of mineral resources, and on the other hand is the cause of 30% of waste, right? What happens to the natural system where these sediments are also obviously created based on natural phenomenon. And actually the effects of taking out these minerals, changing their composition through firing, by mixing them, and then putting them back into the earth, will create new forms of rock. We may call it technofossils. And although most of these repercussions will only be felt in millions of years, there are actually examples in research that already show how lava coming out of underwater volcanoes is mixing with the plastic of the ocean, is creating sort of mixed rocks of plastic and mineral materials. And I think this is quite scary, frankly, to think about what the impact of this is when we just dig up fresh materials and then bury something completely different, right? And so the question that I've been posing myself for the past decade almost is, how can we maybe match these two independent flows, which on the one hand sort of take the resources out of the landscape and then fill different resources back into the landscape? And is there maybe some overlap in the mineral composition of these two minerals that we source on the one side and then dispose on the other side? And I want to speak quite concretely about a project that is very close to here. This is the new construction of the Living Village by the Yale Divinity School. And this is a render that most people look at and don't think much further about, but for an engineer and architect or somebody who's looking into soil surveys, a much different picture is actually painted. So by analyzing the composition of the soil that is under the ground of the new construction, many different factors sort of then determine not only how the foundation works, but also what even is happening with the excavation soil that can be found. If it is contaminated, it must be deposited in a certain way. If it has certain components in it, it can be reused. And to simplify this drawing, I sort of have this schematic diagram of it, where you can see the different boreholes that sort of determine the composition of the soil. And then this is analyzed in order to really understand what we have at site. And the interesting thing about that is, I mean, we're sitting in a basement right now, which obviously means that the soil had to go that was in the immediate place here. But the interesting thing is that if we build a building and seal additional surfaces, we often also have to actually change the soil that is immediately surrounding the building in order to increase infiltration. And so massive amounts of soil are moved as waste through the country. In Germany, for example, is the biggest single kind of soil that we are waste that we are producing. And quite frankly, we were wondering if we could just transform this into a building material. And at the core of this is really understanding why the soil is being moved in the first place. And the reason for this is that most soils are a composition of gravel, sand, silt, and clay. And while we can use gravel and sand for the production of concrete, as soon as we have some form of clay in the soil, it usually increases the amount of cement needed in order to produce a strong concrete. So a sieving analysis of the soil for concrete might look something like this, where we really do not want to have any clay particles present. But we found out that that is exactly the reason why the soil is not being reused. And so we did some research trying to understand what the optimal amount of these different components in the soil would be in order to produce building materials. And these curves looked something like this. So we do have sort of like a gradual mix of gravel, sand, silt, and clay in the soil that need to be present in order to combine them into a mass that can be used in order to produce building materials. And as a proof of concept, we've actually been looking at 3 different places in the world in order to prove that this is actually feasible and doable. And you will see in the next slides always these 3 case studies that we've been looking at. One is in Germany, one is in Senegal, and also most recently here in New Haven with the Divinity School. And by preparing the soil carefully, also sort of mixing maybe different soils from different construction sites to fit into this corridor that I was showing earlier, then sieving out the larger pieces and adding the right amount of moisture, then using a process which is using only mechanical pressure, no additives, no hydraulic binders added, we can actually achieve a building product that can be used in order to build load-bearing masonry. And the wonderful thing is, because it was only produced using pressure, no firing, no hydraulic binders, it is 100% reusable. So even if I do not like the bricks anymore, I can just crush them, re-wet them, and then repress them into new shapes. And in the past year, we've been done a lot of testing in order to understand their performance, compressive strength testing. This is actually here at Yale a couple of weeks ago, where we tested the blocks that we produced from the soil from the Divinity School project, but also immersion tests where we wanted to understand their reaction to water. And we've been able to qualify these bricks, as I said, for load-bearing application, and increasingly been looking also at diversifying their application in different assemblies. So going beyond the use in just masonry, also exploring their potential in ceiling constructions, not only as large-scale blocks, as you see in the center picture, but also, as I'm sure you've all noticed when you walked in this, really symbiosis with timber, where the beams utilize the tensile strength of the timber, and then these bricks are spanning in between as an arch that is only in compression. And we hope that this is a way forward of really connecting two mineral streams that are completely unaligned at the moment, and see a great potential in integrating this globally. And it really shows that just understanding the real composition of these materials that are circulating, their quantities, we can design innovative building products that may cater to the building needs of the future.
Thank you. Thanks a lot, Christian, for this very inspiring talk as well. I'm sort of, I think, maybe yours was less we have here 3 technical applications, and I think the overarching theme is scaling. This is all you're doing. You have like really nice ideas, but sort of how do you get to the next steps? And maybe you want to start, Christine, I don't know, like to get to use, is it education that's needed? Is it, or sort of what other barriers, or is it access to your various data sources? What do you see as the next steps there?
Great, thanks for that question. For sure, education is a big part of it. I think entrepreneurship is also a big part of it. So I always teach my students a bit of what are you going to do afterwards? Are you going to work for a conventional architecture or engineering firm that does the status quo, or are you maybe going to change the way we build things? Sometimes that means that they have to create their own companies that do things differently. So I think we have to teach differently also at universities. We have to teach a bit more across disciplines as well. I think it's a very interesting, you started talking about how you got here, and then talking about that you started in biology, and then working now on the urban scale, which I think it's really amazing to see like the different scales on which you work, but the same principles of something that exponentially changes, and I think that's really inspiring, right? So, and we have system thinkers, material scientists, engineers, architects, biologists working together. I think that is something that needs to happen more, connecting these different disciplines so that we can get new ideas, new technologies, new ways of collaborating with each other so that we can get there, so that we don't stay with whatever we have always known in the past 50, 100 years, but that we go back to kind of deeper knowledge of how to interact with each other. And I really liked what you were saying also in your talk about your grandmother, saying that it wasn't innovative. I think the real innovation is, going back to what we've forgotten about the circular economy. We've always had a circular economy. Mm-hmm. Like I was mentioning a Pantheon in Rome, the bricks of the stones of the Colosseum in Rome have been found in many other places in Rome. as well. And so this kind of, how can we learn again from the past, but in today's society, with today's technologies that are really emerging, having these connections between the different disciplines is really what we need to upscale these principles.
Thank you. And before Eva jumps in, I forgot to say, please, if you have questions to any of the speakers, go to the QR code, and type in your questions, and we will read them to the audience afterwards. Eva.
So to add to that, because definitely agree on the need for all of this interdisciplinary collaboration, but I think one of the biggest challenges that we're facing right now is that we already have such a complex set of structures and systems that also in many cases need to be deconstructed, and there's a lot of lock-in. And in terms of your question around what is needed to really scale and shift things, we already know, most of us working in the space, that there are no silver bullets. It's not like, oh, that one particular problem that we need to fix. It's often many different barriers that are stacked across layers of the system. So there might be capability and knowledge barriers, policy barriers, technological lock-ins, et cetera, et cetera. And if you are trying to drive a shift, you have to figure out a coordinated way of addressing all of them simultaneously. And that's where that collaboration comes in potentially too, where you say, okay, well, as a group here in this room, if we know that we want to shift a system from A to B, from our current linear resource model to a fully circular one, what are all the things standing in the way? And maybe and I've been thinking more and more that it's useful to do that in the context of places, because there you have like these defined boundaries. But the other thing that we need to be aware of is that the system around us is getting more chaotic and unpredictable as we move. And it's actually we can't necessarily count on the fact that things are just going to continue in these projections. And we have to be more prepared for adapting to potentially dramatic shifts around us. And that's I think, one of the biggest challenges that we're facing now.
Jennifer.
I was just going to say as well, I think the thing that confounds me in most cases is that we can all do very complex work. Everyone here is an expert in their field. I step into a classroom of 50 students who are set to graduate next year, and they do not know what recycling is, and they do not know how the economy works, and they do not realize that they have individual agency to do anything about it. And that's not just the students. That is the majority of actors and decision makers that are out there in the world. They know their piece, but we do not have a common understanding of how those pieces fit together. And when you ask the question about education, I think education is a part of it, but we also know that access to education is very disparate, and it's entirely dependent on who's at the front of the room and what they choose to talk about. And I think, so in addition to education, we need to be seeking the creation of a common sense or a common understanding, because we can accelerate to all the technological interventions that we want, but if 99% of the population cannot engage in that conversation as well, we will still falter. And I think that is my personal challenge, and why I also stick with very basic examples in some cases. We have to make this familiar. We know this. This is a human knowledge base, but we have not always done a good job of making sure that everyone's along for the ride. And that means we often have to maybe reduce our, talk differently, use different language, and focus on what is that common ground.
Yeah, I think one aspect also of this is that with sort of the materials of the 20th century, we've lost a little bit the material-specific expertise. And I think materials are designed in a way to reduce liability, because no matter how you use them, they work and they tend to not fail. And I think one thing that needs to be reintroduced, especially into education, is a fundamental understanding of material properties. And I think this is very important for architects. And the way that we've been structuring, for example, the course that we were teaching here at Yale last semester, it started with touching timber and touching earth and just trying to understand how fibers work, how the fibers are acting together. What happens if I add water to the earth? How does it change its properties through that? What happens if I compress it, right? And then understanding how you can use those materials in symbiosis in the built environment, right? And I think sort of there's a danger that we are prescribing attributes to nature-based materials artificially by adding adhesives or over-dimensioning them. and not being able to use them effectively, or earlier the term sufficiency was used. And I think this is really a fundamental change that we have to undergo, to really look at what is the right place for this material in the built environment and what may it not be, you know, and not to project realistic expectations, let's say, towards the materials. And I think that's also true for reuse materials, right? I think also reuse materials have their place, and I think this needs to be something that engineers and architects need to be made more aware of, and I think that will completely change the practice and how we're interacting with our resources, and then also ultimately with the buildings.
Thank you. The question here from the audience for Eva. Regarding you mentioned to the point of scaling that only 12% of virgin material demand can be offset by urban mining. And the question is, if this is a single city scale, how would you expect that to change if the scale was increased to a region or a country?
That was actually on a European scale, that calculation.
Oh, there was a region.
Yeah. However, I have to qualify it and say a few more things about it, because of course that's done based on assuming current growth rates that they're going to continue, so that we have increasing construction demand year on year until 2050 or whenever the extrapolation was till. Because that creates that problem again, that when you have materials getting disposed of, only a fraction of them can be put back into the system, and then your demand every year is increasing, so that percentage stays low. But also that we're not building in a more circular way, that we're not implementing digital technologies to track and trace where materials are, not improving disassembly techniques and policies to support that. So it's under those conditions. It's like business as usual extrapolation. So of course we can get that number up. That requires a lot of coordinated investment, policy, entrepreneurship, all sorts of things to make it improve. But we also have very little time to get it to improve. Mm-hmm. We're already out of our budget for carbon. So it's that's also why I was pointing out that we really need to take this demand side management thing more seriously. We're not going to solve our way out of this problem just by figuring out how to manage end-of-pipe materials. So,
okay, thank you. Another question was for any of the speakers. Sorry, let me just see.
Wow, lots of questions now.
Yes, and they keep that all. Current context tells us that all the actors in the delivery of buildings, that materials are cheaper than reused materials, so that new materials, and that the skills for reuse are quickly dissolving. What about markets, culture, and policy to change this?
So maybe I can start. Mm-hmm. If I understood the question correctly, I think this is really one of the challenges that we were talking about as well, about are we going to do reuse of building materials or of buildings if it's not cheaper than extracting raw materials, right? It's an economical question in the end. And we're not going to be able to count on the fact that it's the better thing to do, so it needs to become cheaper to do reuse of building materials. And that's why we are working on having digital technologies helping us making it faster or more efficient or less dangerous, or having the information in time so that it's cheaper, that we get the materials sooner than if we extract them somewhere else and make them ship to a city because it's right there. Like having all of these technologies helping us to get the reuse of building materials cheaper than extracting raw materials is the only way that this is going to upscale.
Or on the other side,
before somebody else jumps in, there's sort of a related question is on sort of how can you make the circular economy economically competitive? Is it by monetizing externalities through taxation of virgin materials? And as these are politically very difficult to push through, what other means sort of, but again, building on what you just said.
Well, I was literally just saying, of course, there's the whole matter of externalities not being factored in, but there's also from the design side, right?
Yes.
You can actually design things to be very different from the outset to be much cheaper to disassemble. And I think if you combine, so ideally you have a stack of these things where you're costing in some of the externalities, you're making it much cheaper to disassemble and also by doing the design from a different way to begin with. So, go ahead.
There are two different things. The one thing I wanted to, again, this common sense is, common understanding is a price or a cost is a point in time, and we tend to forget that as well. The cost of the very first car that was ever manufactured by Ford was much more expensive than what happened after it had been a perfected economies of scale system. If we don't invest in figuring out how to deconstruct things, have those technologies, we will not accomplish economies of scale. The expectation seems to be, in this moment, if it is not cheaper, we cannot do it. But photovoltaic, solar technology, and wind technology, this is case in point. The last 10 years has proven what that investment does to price. We just have to actually be patient enough to recognize it will take time and then put our money into that as well. The other piece of this, a lot of the work I did on remanufacturing, it really focused on price as a way of reorganizing the operational costs. So manufacturing an engine for a massive off-road piece of equipment or mining equipment is majority materials cost, especially if you're using only raw materials. And efficiency in robotics and automation mean the labor cost is much smaller. It also means your workforce is smaller. Remanufacturing or deconstruction, these other processes reorients that. You are paying far less, 90% less in some cases, for the raw materials going into that. But it is a more complex thing, so your labor increases. But data, time and time again, proves that at the unit level, doing these deconstruction, remanufacturing activities is going to shift cost from materials to labor. And in an economy where we have unemployment and we have these other challenges, especially skilled labor challenges, that's not a bad thing. So we can improve profitability, we can reduce unit price overall, and we can shift from buying finite raw materials, putting that into paying people wages for skilled work and investing in human communities at the same time. And so those are different dimensions. Price is a moment in time, but it also wraps up a lot of other pieces. If we dig deeper under that, we can see that this actually makes a lot more sense, not just from price, but from what it does for us as humans.
And maybe also to add on on top of the price argument, there is also the resilience argument and the fact that so I've been working on circular economy principles for 15 years, and before that, whenever I was saying I work on circular architecture, people literally thought I was building domes and yurts, which is very confusing because I actually do build domes and yurts. But then I saw the kind of discourse changing right about COVID. Suddenly, everyone was starting to talk about circular economy and getting interested in it. And I thought it was interesting that it happened just when we had all of these supply chain problems because of COVID and other things at that time. And then suddenly the price of wood increased crazily and so on. And suddenly they were like, oh, but wait a minute, we're throwing away this wood. And then we are waiting for 3 months to have the thing arrive that is delayed and that is kind of 3 times more expensive than last month. Why don't we reuse this? And so suddenly there is this common sense that comes back because you have these challenges of delays in deliveries and the price increases and so on. So it's also about what do we have in our city today so that we don't depend on others. And in today's big global challenges that we are facing, I think that's also something that we should really value, that we are a bit more resilient also with the resources we have. I like that.
Another question for anybody, I don't know, maybe Kristen, if you want to weigh in, is more on the quality of our used materials from the building stock and the concern that basically here, since the 50s, buildings have become the stock or a repository of the petrochemical industry, including PFAS from flame retardants, etc. So how do you consider or remove these when reusing them for a second life?
Mm-hmm. Yeah, I think that this thought is interesting because we buy materials at a certain price point and then we build a house and then suddenly the materials don't have value anymore, but the value is completely shifted to the house. which is interesting because then when you deconstruct or demolish it, it's very difficult to reassign value to the materials. And in most cases, frankly, they're worthless or even cost you money to dispose of them, right? And so I think this is maybe also connecting a little bit to the previous question, but I think this is exactly where we need to understand what design can do in order to prevent that, in order to actually keep value to the material and also understanding how maybe the value of the material and not just the value of the real estate as a whole envelope might change, right? And I think people would make very different material choices if they actually would be aware of that, right? If they would be like, okay, like if I use this material, then it will retain its value because I can deconstruct it and resell and reuse when this house may no longer be functioning in the way it was supposed to be, right? And I think this will then also completely change the way we think about using petrochemicals and like dangerous substances that especially cause problems in the deconstruction process, because this is exactly what is causing the value loss to the assets that we actually have.
Which in a way goes back to better separation. So taking the time or making the value that at end of life you still can sort of take the same time and care that you do at the beginning, at the design process.
I mean, it's not only about the design process, but also about the tracking and the tracing or giving an identity to these materials, right? Because if the building owners would have a material passport with all of the materials that they have in their building and what they are worth at that moment in time, they might be thinking twice before they demolish parts of their buildings, right? So it's also about giving an identity to the different materials.
Question for Eva. When you spoke about the floating housing units in Amsterdam, wouldn't environmental building projects like this also be heavily affected by climate change, considering sea levels will rise as time goes? Well, so do the floating houses.
Yeah, that's, I guess, an easy one. I mean, they're great because they are not affected by sea level. So you can have these amphibious constructions, and in the Netherlands, there's quite a lot of just floating buildings. So.
And how resistant are they, just out of curiosity, sort of like storms, high waves, etc.?
I mean, they're really quite stable. They're built on these platforms that are not particularly movable. Though the weirdest thing I learned when I was on the building team of this project is that you do have to really be careful about how you're balancing your key infrastructure, because the buildings will tip if you don't balance it properly when you're, and you have to think about where you put the piano, for example.
Okay, thank you. And a question to Catherine. Was interested in your experience with comfort levels from building owners and users from reused building materials components. And also possibly if you could talk about some of the technical barriers and how they can be overcome, testing for structural integrity at end of life, keeping record of events during a building's lifespan, such as fires, and transportation of materials.
Nice, yeah. Thanks for that question. Well, so the comfort levels, I imagine, like, so there is a lot of, so I live in Switzerland, and there's a lot of rules there for operational energy, which is then related to comfort levels. So we have a label called Minergie, which is a bit like LEED or something like that, that requires us to have like super insulated houses. And what happens a lot is, because we need to attain these levels of comfort, we just demolish the existing structures that are there. The beautiful Swiss chalets that we have there get just demolished, and we build apartment blocks instead that are very well insulated for the comfort levels that are in the norms. And then you cannot open your window because, so there's a lot of challenges with that, and a lot of what happens a lot in Switzerland, and I think also in other countries, is just houses are being sold as building plots. So with the inconvenience that you mentioned, that you still have to demolish a building, instead of thinking of like, how do we renovate this house so that we don't have to rebuild the whole structure, which is like the biggest part of the embodied carbon of a building. And maybe we don't have to have the Minergie's best standard or the LEED's best standard of operational energy if it means that we renovate reasonably so that we have a reasonable operational energy consumption, but that it's still comfortable, but we don't have to spend all of the embodied carbon in demolishing and rebuilding. So there is a trade-off that needs to be calculated, and almost every case study that I calculated a trade-off between is it worth it from a life cycle perspective to demolish and build new with the very, very well insulated buildings, or to just renovate, retrofit an existing building. It was almost always better to just retrofit when you do a life cycle analysis. So just doing the analysis would be already a first step in the decision-making process. But it's very difficult to implement that on a policy level, because there is not a one-size-fits-all for buildings kind of policy. And when you do a policy, it needs to be the same rule for each building, but the problem is it's very, very different from one building to another, from one building user to another. Also, what is important in terms of comfort, in terms of consumption, in terms of use of the building, so in terms of the climate in which it is, the environment, the orientation, everything is different from one building to another. So it's very difficult to make policies that are like really doing. And then the second part of the question, I don't know if I answered that.
We are almost out of time. However, maybe in 1 minute, if somebody could super short bring us back to our trees in the room here. Given the pressing challenges of deforestation and the limited availability of responsibly managed wood plantations in these regions, how can circular economy principles, design for disassembly, material reuse, be effectively integrated into wood-based systems? Not sure, maybe Christian or Eva.
In one sense, okay. I mean, what we were talking about, there's, first of all, prioritizing the highest value use and really looking at the whole system in terms of tree species, plantation management, looking at climate change resistance, because that's also part of, for me, circularity as well, is looking at the provenance of these materials and ensuring their long-term health and productive, and also then making sure that you're optimally using it. We've already seen great examples of prefab, reducing the construction waste. There's all of that in one package, but you have to have like an integrated value chain perspective and multi-life cycle perspective.
Thank you. Thank you very much to the panel again for sticking here. Thank you.